Okay, so it's now recorded. Uh,
Good.
yeah,
Thank
and
you very much.
sure. And so you were faced with these two things, this equation here, and the other equation, which was f of some lambda x is lambda f of x for all x in this vector space. Now, the first thing is also called sometimes that f is additive. That it's an endomorphism uh, with respect to plus. And this here is a condition which is often called that f is homogeneous. And one thing is that we might check if these two things, well, in some way are independent or not. So the first thing is uh, if this holds, so maybe the additivity implies the homogeneity, and conversely, and if this would be so, then it's unlikely because then one usually would require only one of these laws. But in order to tease you, let's try in an example. Let's take uh, a vector space V, maybe the real numbers, as a one-dimensional vector space over itself. And suppose F is additive, then we might look if F is also homogeneous. Now you can say if F is additive, then you have F of x plus x is equal to F of x plus F of x. Which means that F of 2 times x is 2 times F of x. And the same, of course, works for 3 or 4 and so on, even for coefficients in the negative coefficients. So we have this, that uh, f of z times x is equal to z times f of x for all z in the integers. And this means that we have almost something like linearity or homogeneous map. Now let's try with 1/2. Uh, if lambda is 1/2, you can still say that f of 1/2 times x plus 1/2 times x, which is f of x, and since it's additive, it's, let's make it short, 2 times f of 1/2 times x. And so we see that we also can take out the fractions. What works with 1/2 works with every rational number. And so we can even improve this, what we had here. That this holds for all z in the rational numbers. Now this is pretty interesting because for infinitely many set, we can say that f of lambda x is lambda f of x. But now at this point, I have to stop because I can't know how to work with irrational numbers, and we'll see that we have almost reached homogeneous the homogeneous property, but not quite. Of course, if f is also continuous, or if you have some other condition, you can work further on, because if it's continuous, then f coincides with the homogeneous maps on a dense subset, and so it's identical to this. But without continuity, you cannot work on very much here, which brings us to the first thing. The first thing is the first homework question, question 1. Find some function f from the reals to the reals, which is additive but not homogeneous. Now, I sometimes put in some questions for you as homework exercises, and I think it's good to do something by one's own, because if there's a well-known statement, if you just look at people doing mathematics, you will become very good in looking at people who are doing mathematics, and this is not
Sorry. I was trying to.
And well, I've heard some other motivation, which said that.
Oh, okay. So. Oh, okay. So I will try to come earlier then. That's not a problem.
Okay.
Okay, that's fine. So I have to attend something, so we'll talk later. Okay.
Yeah, and I've also heard another statement
Okay. Right.
that doing mathematics is the same as doing sex. Watching is nothing, doing is the only right thing. And so it's much better to do something. And we'll go back to these questions in 1 week later, all the time, and discuss maybe what's known about these things and so on. The next thing is that we might look if the other implication works. Well, f of lambda x is equal to lambda f of x. Thus, this implies additivity. And again, let's take f to be a map from the reals to the reals to make things easy. Which is homogeneous. And we look at f of x plus y. Now, we have to distinguish two cases. If x is equal to 0, in this case, if f is x is equal to 0, then we have f of y here, and this is the same as f of 0 plus f of y, because f of 0 has to be 0 if you by the homogeneous property if you take lambda equal to 0. And so we see that in this case this equation works. But if x is unequal to 0, then we can say f of x plus y. We can compute it in this way. Now there is some lambda, namely take lambda equal to y divided by x, and you can write this as f of x plus y divided by x times y, and this is equal to f of 1 plus y divided by x times x. And now, by the homogeneous property, we can work this out and say this is 1 plus y divided by x times f of x. And now you can work this in. You get f of x plus y divided by x times f of x. And by the homogeneous property again, this is f of x plus f of y. So incredible. I hope I could make you a bit unsecure if you don't know the story yet, that maybe every homogeneous map has to be additive, and so it would be a linear map altogether, and we can forget about the first law. But maybe this is only true in this small example, and hence, of course, I have the second question, if this holds in general. I've explained this. That's a nice pasty sponge. Very good. And so question number 2 would be, find a homogeneous F which is not additive. So we have now two kinds of functions which are in some way close to linearity. These are additive functions and homogeneous functions. And we might take all of these maps together to get some collection of maps. And the first one, if we take all endomorphisms of this vector space, then we what we get is something which is called end B. And for that, we only consider also here, when I spoke for endomorphisms, we only consider maps which go from V into V. And if you look at this, there's not much about being a vector space here, because in this case of linearity, the additivity here has nothing to do with this lambda on the right-hand side. And so you can forget about the thing that V is a vector space. All you need is a group. And so we'll write a G here, such that G plus is a group. And if you have a group, then it might be abelian or not, but we'll come back to this point later. And we have another thing which we can take here, H of V. That's a collection of all homogeneous maps from V into V. Now for that, you certainly need a vector space because you have to take this, or maybe you have a little less than a vector space. Maybe what you have is, excuse me, what you have is perhaps something else. You can take some module M, so that M is an R module. And in this case, things are pretty much the same for a while. And what we get is something we don't really know which structures did we build up. Note that every group which is abelian, every abelian group is a module over the integers. So R modules are pretty general. They include all abelian groups. And so we have these two collections of maps. And now we might want to find out if they have some structure or so. So for instance, is end of G itself a group or something else? Most of you will know that it's a ring sometimes, but not always. And we will simply check if this end of G is an additive group. Well, for having a group, we have to define this plus because we have the plus just defined on G, and we define the addition, of course, in this way that two endomorphisms F plus G work on some x as f of x plus g of x. So it's pointwise addition, and we can start to find out if this, yeah, usually sometimes students, but also professionals forget about the most important thing to find out if before they start with associativity and so on, they don't look at this thing if this is closed altogether. So if the sum of two endomorphisms is really an endomorphism. And for that, we now have to take, we now have to check what's going on. And we'll do this step by step because it's essential to find out why it works sometimes and why it does not work sometimes. So let's start with F plus E. Now, and apply this to x plus y. F plus g of some argument x plus y is just the sum f of this plus g of this. So by definition of the addition which we have here, this is f of x plus y plus g of x plus y. Okay, now we can apply the knowledge that f and g are additive, they are endomorphisms. So we can say this is x plus y, excuse me, f of x plus f of y, and here plus g of x plus g of y, because f and g are additive. Okay, and then we perhaps make a little stop to find out what do we want to know. We want to know if this f plus g is an endomorphism. So we want to know if f plus g of x plus y is f plus g of x plus f plus g of y. So let's write this down here. Now we can proceed and we find out if we reach the same goal here. F plus g of x is by definition f of x plus g of x, and this here is by definition f of y plus g of y. So did we arrive at the same point here? Now f of x, that's fine. The last g of y is also fine. But here in the middle, you see, we have f of y plus g of x, and we have g of x plus f of y. So you see, if the addition is not commutative, then we're in trouble. In this case, we arrive at two different expressions. Well, maybe these are not so totally different. And so the question 3 would be, find f and g, which are endomorphisms additively, but f plus g is not an endomorphism. So I don't know if, can one see this far end of the board? Looks like, yeah. Yeah, and so we see that we get here a group. Yes, we get a group, but only if the addition in G was abelian, and then we can make say for sure that also end of G has an addition which is closed, and so we can check the next things. The next thing is associativity that goes without trouble because of the associativity of the addition in the group. We have the zero map as the neutral element, which is also no surprise since it's an endomorphism. But we get again some problems with the subtraction. Namely, if f is an element of end of G, what about minus f? And as usual, the best way is not to speculate. Is the best way is simply to come to test it. So what is minus f of x plus y? Now minus f of x plus y means that we take the whole thing f of x plus f of y in the negative. So it's minus f of x plus f of y. And so you know how to compute this. This is minus f of y minus f of x. Is that the goal we wanted to reach? Well, we what we want to have is that minus f of x plus y would be minus f of x minus f of y. And again, we see here this discrepancy with minus f of y minus f of x, and here in the other order, which means that again we would have a contradiction. Minus f is usually not an endomorphism, except if the addition happened to be abelian. And so we see we get all kinds of problems here unless we have an abelian group to start with. And so we must be careful. End of G is usually nothing, no algebraic structure, it's not closed. And well, we could take also something into account which can help us here, because if you have two endomorphisms from G into G, then you can also, instead of adding them, you can also use substitution. You can take the first endomorphism first and apply the next one to it. It's still an it will still be at least a map from G into G, and we denote this by F composed of G. This takes X first to G of X, and then to F of G of X. Now it's a bit strange and a bit awkward, and that's just the way how we write functions, because if we take this, it looks like if we first apply f and then g, but that's not true. We first apply g and then apply f, and so the order is reversed, and so sometimes one calls this f after g. And then this word after makes it clear what we mean. Yeah, and the thing is that we can also choose to write functions the other way. We have decided here to write f of x, or the function applied to x. That's customary in most areas of mathematics, except in group theory. In group theory, many group theorists prefer another notation, x and then f. This has the advantage that if you have two functions, f and g, and then if you apply first f and then g, no order is reversed, and so we don't call this f after g, it's first f and then g. This things are, as I said, quite customary in group theory, and in other areas like in analysis, it's not the case. You rarely see the notation x sign or the sign of x, uh, because that brings up some other things, some other confusion. And so, well, we can work with both of these. And in fact, the philosophy behind these two ways to write this are different. Here, you first start with an F, and you have a pool of many things, of many x's and y's, elements of the group. And F simply waits until it can catch some x and makes transfers this x into y. Uh, uh, so F is standing there waiting for a victim x and transferring it. Here the roles are different. Here x is there first, and x waits for the bus. Bus is F, which brings this x uh, to some y, if this is equal to y. So here F is the starting point of the story, and here X is the starting point. And yeah, one cannot say one of these uh, ways to write things is better or worse, but maybe we'll stay with this way of writing. It might be more familiar to most of you. Okay, what happens now if we take two endomorphisms and compose them? Now, you can almost see with your bare eyes that if we take f composed with g and apply this to x plus y, we have an x plus y here first, and we can make it to g of x plus g of y because g is an endomorphism. And then f of a sum is the sum of the f's. So it's no problem to see that f composed with g is again in end of g. And since composition of maps is associative in general, we know that at least endomorphisms of G with respect to composition is something which is called a semigroup. And in fact, it's a monoid because with a neutral element, the identity map is always an endomorphism. And so at least we can say that uh, that this is at least a monoid, which means that it's closed with respect to composition, is associative, and has a neutral element. Of course, we cannot expect that every endomorphism is invertible, and so we don't arrive at a group here. But it's quite interesting that this happens independently if G is abelian or not. So the abelianness of G is no real obstacle here. And we get something which is, yeah, close, at least close to a ring, provided the end of G is a group. So provided G is abelian. Now, for a ring, we have to have some other laws to be fulfilled, namely, there must be an interplay between plus and the composition here. And this interplay is usually done by the distributive laws. So let's check the first distributive law. This first one would be f composed, f plus g composed with h. And we would like to find if this is the same as f composed with h plus g composed with h. And for that we simply take some x and find out what happens with this. Now, this is f plus g after h, and so we have to apply h first, and we have f plus g of h of x. And now we have to apply the definition of addition. And so by definition here, it's the same of f of h of x plus g of h of x. And from that you can see immediately here that this is nothing else than f after h plus g after h applied to x. And so what we see, this distributive law holds, and everything holds by definition. And if you look closely, then you have seen that we didn't even have to apply some property of the group G, and we didn't have to apply, let's look at this closely, that F and G are additive, because here that's just a definition of composition, and here this is just a definition of addition of functions, and we make everything converse. And so you see that this applies not only to endomorphisms, but to all maps from a group into itself. This distributive law holds all the time for all, even all maps F, G, H from the group into itself, which is quite remarkable. And yeah, but we shouldn't forget the other distributive law. This is easily forgotten. When I was in high school, we had a textbook for many, many years in mathematics, and this said, proof, or it showed that this distributivity holds. And then the author said the other distributive holds in the same way. And it was never corrected for centuries or almost. But let's look at the other distributive law. And this would be F composed with H plus G. That sends X into, okay, we have to apply H plus G first. We have H plus G of X. And then we have to apply F to all of this. Well, that's now just by definition of composition. And now we again use the definition of addition. So this is f of h of x plus g of x okay. Yeah, and now you need additivity of f. You can see this, and the additivity of f would allow us to write f of h of x plus f of g of x. But in here we get f of h of x plus f of g of x only if the addition here is, or if F is additive. We need really this property of having this function additively, because otherwise it would not hold. So we see all kind of troubles if we get a little bit away from linearity. Here linearity would solve everything. And in the case of linearity, you really get that end of G plus is a group. This is a monoid. Both distributive laws hold. And so what we get is some well-known result that if G plus is an abelian group, then end of G with plus and composition is a ring. And in fact, these endomorphism rings, are very prominent because they are what's sometimes called Catholic. Class of rings, and this means that Catholic means all including and similar things, and it means that every ring can be embedded into a ring of this type. So more precisely, for every ring R, you can find an abelian group G, such that R can be embedded into the endomorphism ring on G. So these types of rings are really interesting, well-known, and important. And we see that as soon as we get away from the case that we have an abelian addition, we run into some troubles. It's not only, it worked fine here with the endomorphism with respect to composition, but in addition we had troubles and the whole thing was not even closed. And so we see that if we take just this property, we lose a lot of nice properties from ring theory, which sometimes would be desirable, but we will come close to rings again, and we have to repair a bit from this. We'll do this later on. The next thing is, what about the structure of the homogeneous functions? Now, for the homogeneous functions, we can make the same tests, and we'll look if we again run into trouble. And I'll promise you it will be not so troublesome. But before we continue, I would like to ask you question 4. Find an example. No, I'll wait for that. A moment. Let's do, as promised, the homogeneous functions on a vector space or a module And let's do it for marshals right away. So I would like to write this in such a way that we have R marshals, because the elements of R, they act as these lambdas, which can be multiplied with elements in capital M. Of course, we can also use addition, and to find out what this structure will give us. Now, the first thing is that we have already bad memories from the endomorphism story, and so we'd better check if that's closed at all. So let's take again F plus G in this collection of homogeneous maps, and apply this to some element X, and to find if this is again if this F plus G is again a homogeneous function. So what do we have to test for F plus G to be homogeneous? We apply it to some lambda X. Now, where lambda is an element in R, and where X is an element in M, later on we'll write R and M, but this is so familiar and close to the case of linear algebra that I'll do it. I would like to do it this way first. Okay, so what can we do now? The first thing is we have the definition of addition here. And by definition, it's just f of lambda x, and then plus g of lambda x. And now things turn out to be easy. It's running by itself to write this as lambda f of x plus lambda g of x. And here we can put out the lambda and write f of x plus g of x, or what's the same, f plus g of x. And so we see, yes, if we can pull out the lambda in f and g, we can also pull it out in the addition. The next thing is, what about the associativity of addition? It's always associative. The zero map is here. What about minus? That was a crucial point before as well. What about minus f? Is this again homogeneous? And minus f, we apply it to lambda x. And we see what does this mean? Minus f is just minus f of lambda x. And f of lambda x, okay, we can simply write it as lambda f of x with a minus before. And now we are already quite good the way, because we can also write it as lambda times minus f of x. And so we can write it as lambda times minus f of x. And we see if we can pull out the lambda for f, we can pull out the lambda also for minus f. And so, yes, we can say this is a group. And since M is a marshal has abelian addition anyhow, we can readily say that we get a group. And it's very easy to see that this will be an abelian group. And so that's fine. We have much less trouble in that. Yeah, yeah. Okay, and so we see that without any further restriction, the homogeneous maps do form an abelian group, and we can be very happy with this result. At least we always have a nice structure of an abelian group. Now the next thing is, what about composition? Again, since we map here the elements of M into elements of M, we can repeat it and we can study the composition. And again, we have to find out if the composition, this is closed with respect to composition. And so we apply F composed with G to lambda X. What do we have to do first? The first thing is, what is F composed with G? That is F after G. So it's F of G of lambda X. And now things are running by themselves again, because here you just cannot avoid to pull out the lambda here, and we get F of lambda of G of X. And here again, it's just too resisting to stop here. We pull out the lambda, so we get lambda times F of G of X. And this is nothing else than lambda times F composed with G of X. And we see that if F and G are homogeneous, then F composed with G is also homogeneous. Yeah, that's wonderful. So we have also a closure with respect to composition, and we can find out what about the next thing, associativity. But composition of function is always associative again, so we have no problems. And what about the two distributive laws? Well, we have seen one distributive law, namely that was in our case that F plus G composed with H is equal to F composed with H plus G composed with H. This holds all the time. We have, for that, we had no requirement whatsoever. It was very easy. We simply took the definitions of composition. We simply took the definition of addition, and that was enough to show this. But and if you remember, for the other distributive law, we had trouble because that only worked if the first F here happened to be additive. And we see that here we don't require additivity, we just require that the maps are homogeneous. And so we just lose one distributive law, which means that in here, if we add composition, all requirements of a ring are fulfilled except one single thing. This is the other distributive law. And you see that the other distributive law has to do with the fact that the first function f has to be linear, additive, and homogeneous. And so you see that these two different distributive laws are by no means equivalent. The first distributive law, this one, holds all the time without restriction, while the other distributive law is a sign for linearity. And so we see that, which is quite interesting, that there can be all results, all requirements, excuse me, of a ring fulfilled, but with one exception, and this is the other distributive law. So we get that F composed with G plus H is in general not the same as F composed with G plus F composed with H. And so we get almost a ring. We're very near to a ring, and hence we call this a near-ring. And that's the topic of our course now, of course. And we'll see that two things always interfered. In this case of endomorphisms, the other distributive law was no problem, but the commutativity of addition was the problem. While in this case, we only have a problem with the nonlinearity of the function f here. So we make a definition now named to include these things, and the definition would be, since we're near to rings, the near-rings, and I give the definition in this way, that n plus, let's write it this here, it can mean composition, not necessarily, that this is a near-ring. If n plus is a group, not necessarily abelian, and n with composition is a semigroup, which means that it's close with respect to composition and it's associative. And we have just one distributive law that F plus G composed with H is F composed with H plus G composed with H for all F, G, H in N. So we don't require two things from the axiom set of a ring. We don't require the commutativity of addition, and we don't require the second distributive law. So what do we have got so far as examples? We have an example namely H of Rm with respect to addition and function composition. And function composition will appear so often that we also write in the general version of a near-ring this little circle here. So this, the homogeneous maps on the Marshall do form a nice near-ring. And an example of the other type would be the endomorphisms, but they only form a near-ring if the group is abelian, and if not, they form nothing, not even a near-ring. And so we see that two axioms of a ring are missing, and what we suspect from now already is that rings always stand for the cases of linearity, so to speak. We have had the endomorphism rings and also the case that every ring can be embedded into some endomorphism rings. So that means that rings describe in a way linear situations, while near-rings, due to the fact that we don't have the second derivative law, near-rings always describe essentially nonlinear situations. This means that we have in the transition of from rings to near rings, we have the transition from linear situations to nonlinear situations, and everybody who has already worked in cases of uh, nonlinear situations, that this life is not that easy there. In fact, most things in our life, in our world, are not linear. So one might say it's much more natural to consider nonlinear maps. And here we have nonlinear maps from a marshal into itself, and we can give many, many more examples. Uh, Another example would be that we simply take all maps from a group into itself. We call this M of G. These are all maps from the group into itself, sometimes written also as G up to the G power, all maps from G into itself. If G is abelian, the addition here is also abelian, but that's not required here. We just have to have a group, and it's very easy to see that all maps are also nearing. And here we have the homogeneous maps, so we see that they are what's called a subnearing of M of G. And it turns out that M of G is not only a certain class of nearings, it's also a Catholic class. In the sense that every nearing can be embedded into such a nearing of this type, which means that for every nearing n, that you can find a group G such that n can be embedded into M of G. Embedded means you have a monomorphism from this ring into this nearing into M of G. Yeah, then there are some many others, namely you can take, we'll use this later on very often. We can take only M naught of G. These are all functions f from G to G, such that f maps 0 into 0. Of course, you can have many functions. If they're arbitrary functions, uh, why should they map 0 into 0? Sometimes they do, as we have here in the case of homogeneous maps. They always map 0 into 0, as we have seen before. But in the case of general maps, that's not necessary. If this is true, we have, as we see later on, a much nicer life than in M of G, but we can work with both. In some way, the opposite of these maps here are MC of G, the set of all functions f from G to G, such that f is constant. So we have all constant maps. Of course, that's not a very interesting type of nearings, because it simply means that you have basically the group G again, and it maps every element to some constant. There are some other very natural examples. Namely, more examples are given this way. Suppose G has a topology on it, as a topological group, then we can take M all continuous maps from G into itself. Which is also a nice object of study, but for some reason the continuous maps on the topological group have not by far not be so intensively studied as other types of nearings. And another thing would be the following: take a ring R and take P of R, namely all F going from R to R, such that F is a polynomial map.
Yeah.
Now, in the case, say that R is the field of real numbers, the polynomial maps, they are continuous, and so this would be a sub-nearing of the nearing of all continuous maps on the rails. But in other cases, we have these polynomial maps, and that's fine. And usually one takes as the ring R a commutative ring with identity in order to avoid some problems, but we will overcome this requirement later on. A similar type of nearings would be R of x, the polynomials over x. And you might say, well, polynomials and polynomial functions are basically the same. Well, for the reals, we have seen and learned in high school that the polynomial maps and the polynomials really basically are the same thing. But for other rings R, there can be a difference. Simply take the following example, or take the situation that R is a finite ring. Then there will only be finitely many maps from R into R, and so there will be only finitely many polynomial maps. But there will be infinitely many polynomials, namely 1, x, x squared, x to the third, and so on. And so this can be a big difference. Later on, we'll find out what's the borderline, or at least we'll discuss this. What's the borderline that R can be in order that polynomials and polynomial maps coincide, and what other things can we have that they really differ? Now we have found quite a number of examples of nearings, and now it's time for question number 4. Find a nearing. I always abbreviate nearing by NR, nearing N, which is not a ring. But where both distributive laws hold. So find a nearing n with both distributive laws, which is not a ring. These nearings are called distributive nearings, naturally, and maybe they are rather hard to find, maybe not, and it's a good idea to look for an example of this. Now, for the whole lecture, you will get some material sent by email, and it's basically from a long article I wrote many years ago. That's the handbook from the Handbook of Algebra uh, by Michael Hasewinkel, and but I would not. I don't want to send it to you right now. I will send it to you 1 week later because the solution of this question is in there, and then it's no fun to work at this if you have it. So please wait 1 week and you'll get the manuscript. Uh, yeah, also I have to excuse for my bad handwriting. The board is not stable enough. It uh, moves back and forth a bit, so maybe I'll reinforce it for next week. And yeah, and also an excuse for my bad handwriting is that I had a bad handwriting all my life from the first class in elementary school, and also another excuse simply is that I'm an old man, and old men can sometimes have a bad handwriting. It reminds me of a story of a colleague of mine from the physics department. He once went to a lecture in Germany of a physicist who was very famous. His name was Hund, and he was 102 years old. And so he uh, said, I can still speak quite normally, but my handwriting has become so bad that I have to ask somebody of you from the audience to do the handwriting for me. And so he pointed at one participant of his talk and said, young man, please come out and do the writing for me. And the young man got up and said, yes, Professor Honda, I will gladly do this, but uh, observe that I'm retired already since 15 years. So he was not that young as a man, but much younger than 102 at least. Yeah, that gives a number of good nearings, and we can now start to dive into the theory of nearings and get some very easy properties out of this. And so let's say this here. For every nearing, you find some important substructures there. Uh, and the first thing is this. So if n is a nearing, we might take n sub 0, and this is defined as all elements of n, such that n composed with 0 is 0. Now you have seen this before in the example which I just erased, I'm sorry, of m naught of g, all functions which map 0 into 0. And this is also this circle can mean something else than composition, but it's very suggestive to use this, and you see that this mimics the all maps if n consists of maps which map 0 into 0. or the other one is n sub c. All n such that n composed with 0 is n. And we call this the first one the zero-symmetric part, and n sub c the constant part. So this is zero-symmetric. This is the constant part. You might ask, why do we take n composed with 0 and not 0 composed with n? Well, 0 composed with n is easy, and because 0 composed with n, you can write this as 0 plus 0 composed with n, and this is the right distributive, the distributive law which we have at hand. So we can write it as 0 composed with n plus 0 composed with n. And from this you can see that we can cancel this on one end. And so we see that 0 composed with n is always the same as 0. This is a general law in Near-rings. 0 composed with n is 0. But n composed with 0, we would have to use the other derivative law, which we don't have at hand. And we have no other way than to say some elements can have this property, some others don't have this. Now, zero-symmetric means that n composed with 0, as we have seen now, is the same as 0 composed with n and 0. So 0 acts symmetrically on both sides, making the composition equal to 0. Less obvious is why we call these elements here constant. Now, what happens to justify this name? What happens if n is constant? Then we get for all m in n, we can say that n composed with m, and since n is constant, we can write this as n composed with 0, composed with m. Note that we have associativity guaranteed by the property to have a semigroup, and so we can write this without parentheses, which makes life easier. Yeah, and now you see that n, that 0 composed with m, that's always 0. So we get n composed with 0. And n composed with 0 is just n, since n is constant. And now this line justifies the name constant Near-ring, because it means n composed with any other m will always give you the n. This also means that we can make every group into a Near-ring by defining the composition of two elements. This should always be the first one.
Mm-hmm.
So this will always turn a group into a Near-ring. And so we see that groups are a special case of Near-rings. We can say that every group can be made into a Near-ring, and in fact it can be made into a Near-ring in different ways. Well, and of course we call the nearing to be zero-symmetric if if n naught is the same as n, and we call the nearing to be constant if n is equal to nc. Later on we'll see that these two things are really these sets are not only subsets of n, they are always sub nearings. They're nearings by themselves, and we can see next time that every nearing is in some way composed of these two parts. So one can in some way split the work. If one has to work with the general nearing, we can split into the work working for zero-symmetric nearings, which make things much easier, and constant nearings, which make things much easier. And so this is a very good trick, and we'll start to do this then next week on. I think the time is more or less over. Let's stop here at this point, and I thank you very much for attending. I hope you could read something from the board. When I would look at my picture, I see just a bright spot in here. I'll try again to find out if I can improve the situation, maybe with some other lights. But yeah, I excuse for my handwriting.
That's fine. It's okay.
No problem.
No problem, yeah.
No problem. Thank you. That's very polite.
It's fine.
No, I also can read everything.
Yeah. I'm very surprised about that because all my life people told me they cannot read my handwriting. But if you say that, I take your word, and I'm happy about that. So it was good to have you here. Hope you had for the visiting participants. I hope you had a nice trip to Austria, and I hope you can travel to Austria next week again. Uh, for for this, you don't need any visa or any requirements as a quarantine, and I think that's perhaps the only positive implication of the coronavirus. It really enhanced Zoom conferences, and without the virus, I think we would not have had a conference like that. And so let's see how it works out later on. And again, thank you for coming. Have a safe trip back home. Thank you.
Bye-bye.
Goodbye.
Bye.
Bye. Thank you, Prof.
Goodbye.
Goodbye.
Thank you, Professor.
Oh, Prudence, good to see you.
Okay.
Thank you.
There were really a number of people I haven't seen for a long time. Bye-bye.
Bye, Gunther.
Bye-bye. So I also finally I made it to Manipal to come to you in this way. Bye-bye.
Thank you. Good night.
Thank you. Thank you very much.
Thank you. Bye-bye.